Okay, greetings everyone. We will start slowly. Okay, I think the recording still needs a bit. All right. So greetings everyone. We can now slowly start with today's solution session. Today we will have an individual contest solving 8 tasks. This was a contest that was used in 2009 at our school as the school selection contest. The best people out of this contest were advancing to the regional contest. And basically they had similar, slightly worse results than you do. The best guys did also solve 7 problems out of these 8, so you did well. Right now I will talk about the problems, and as before, if you have any questions, feel free to interrupt me and to ask them. So, probably the easiest task today was the task with the inversions. So, the goal is to construct one permutation with a given length and a given number of inversions. So, the trick is to realize if we start with a sorted permutation, we get 0 inversions, and now each time we swap 2 of the numbers, then this produces an inversion. So we can start and go swapping the numbers to produce more and more inversions until we get to the sequence that is sorted in the other direction, n minus 1, n minus 2, and so on. And this sequence has the maximum possible number of inversions, which is n over 2. Each pair of numbers in this final permutation is an inversion. So you can get any number between 0 and n over 2 inversions. And there are different ways how to construct such a permutation efficiently. One way this can be done is, for example, note what happens if we start the permutation with the number k. This immediately produces k minus 1 inversions, because somewhere here will be the number 1, somewhere will be the number 2, and so on until k minus 1 in any order. But each of these numbers will produce an inversion with the number k. So this helps us to construct the permutation a number at a time. What we'll be doing is we take the number of inversions we want to have, k, and we compare it to the number n minus 1, because n minus 1 inversions is the most we can get in this way by placing the number n in the first position. So if k is at least n minus 1, we have nothing to lose by starting the permutation by the letter n, by the number n. So right now we have the numbers 1 to n minus 1 still to place, and the new number of inversions we need here is k minus n minus 1. And we can apply the same process over and over again until we get to the opposite situation when k is less than n minus 1. And in this situation we will use the number k plus 1. This will produce exactly k inversions. And for the rest, we don't want any inversions, so we sort the remaining numbers and output them. So in this way, the task can actually be solved in linear time. We are going from n downwards, placing the numbers, counting the number of inversions, and when it is sufficient, then we terminate this process and sort the remaining values. Any questions? Nope. Everything clear. All right, the second easy task of the day, at least if you know some data structures, was the square count. So what we are given in this problem is a collection of lines. Some of them are horizontal, some of them are vertical. And we are to count squares we see in this picture. So the only trick in this problem is to note what is a square. A square has 2 equal sides. So in order for these 2 lines and these 2 lines to determine a square, their distance here must be equal to the distance here. So if we have h horizontal lines, what we can do, we can take a look at all pairs of horizontal lines separately and record distances we see into a multiset, for example, or into a map or something. And we can do exactly the same thing for the vertical lines separately. So we have a set of distances that can be seen in horizontal direction. We have a set of distances that can be seen in vertical direction. And now all that remains is to pair them up. So we can, for example, go iterate over this, and for each of the distances, check how many times it occurs in the opposite direction and that many squares it generates. So probably the easiest way to implement this, the shortest code, would be to store a map, to take a map, int. So for each distance between two horizontal lines, we record the number of times we have seen this, and then we process the pairs of vertical lines, and each time we take a look into the map and add the value to the result. But there are plenty of other ways we can generate all these into one array, generate all these into another array, and then sort the arrays and traverse them somehow. But using the map results in the shortest code, in my opinion. All right. The next task, in order of number of times it was solved, was, I think, the school task. All right, so this was an exercise in prefix sum tricks and array manipulation and so on, and it had, I think, all of the basic tricks inside. So first of all, what we had to do is to generate the first n primes. The idea is that the nth prime is approximately equal to n times natural logarithm of n. So we can take a reasonable guess where the boundary is until which to look for the primes. This is actually something we can do on our own computer and then check whether the program found enough primes. To find the primes, we can use the sieve of Eratosthenes. So we just go over the primes in the order we discovered them, and each time we find a prime, we cross out all its multiples. Does this make sense? Yes, I don't have to go into details. All right. So after the first step, what we get is an array, let's call it P, containing the first n primes, 2, 3, 5, 7, and so on. And right now, if we have such an array, what we will need to do sooner or later, we will have to be able to compute sums of parts of this array. So for example, this can be one query. What is the sum of primes between here and here? And in order to answer all of these queries efficiently, what we can do is we can compute the prefix sums of this array. So we take a new array that will be one cell longer, and we will compute the sum of first 0 primes, which is 0, sum of first 1 prime, which is 2, 2 plus 3 is 5, 5 plus 5 is 10, 10 plus 7 is 17, and so on. And this is a very common trick, but it is very useful in order to compute the sum in any part of the array. Like this, we take this prefix sum, which is the sum from here to here, minus this prefix sum, which is the sum from here to here, and this minus this is the sum of the numbers in this segment. So once we have computed the prefix sums, we can compute the sum of any segment of the original array in constant time. This trick is very useful, and it can also be generalized into 2 dimensions. This is something you can also encounter in many problems, that you can do 2-dimensional prefix sums. So if you have the original array, then you can compute a new array where each cell contains the sum of this rectangle, starting in the upper left corner and ending at the current cell. And using this information, you can then compute the sum of any rectangle, because the sum here can be computed by looking at this cell, which is this sum. Then you look here and subtract this. Then you look here and subtract this sum. So you got now this minus this, because you subtracted this part twice. So then go there and add this area. So this is how the prefix sums work. And using them, we can, for any segment, say the correct sum. So this can be used in the school problem to process the missing children. For each child that is missing, we can compute in constant time the value it would receive. And now what we need to do in order to solve the rest of the task, we need to find the sum that would be computed if no child was missing. And here comes another basic combinatorial trick. If you are computing any sum and you don't know how to do it, what is worth a try is reversing the order of summation, so summing it not by rows in the matrix, but by columns, for example. In this case, what we can do, for each of the primes, we can ask the complementary question, how many times will this prime be counted? So let's take a look. So, which of these kids will count the prime 2? So, the kid here will start at the first prime and end at the first prime. The one here will start at the first one and end at the second one, and so on. So, all of these children will count the prime 2. This one will start at the second prime and end at the first one, so yes, this will count it. But this one will only count the second prime, so no. And so on. So if we take a look at the prime, at the first prime, these are the only kids that will count it into their sums. In general, for example, the third prime would be counted by these kids, and then by these ones. Or is it the opposite ones? Yeah. So we start at the 3 and continue on. All right, let's do this properly, because I'm starting to get lost. So it may be easier to mark those that will not count the number. So here at the bottom, we have kids that sit in rows 4 to 7 and columns 4 to 7, so their intervals will start with a fourth prime or larger and end even farther. So these ones will not count the third prime. Similarly here, these ones will not count it because they start and end too early, and the rest will count this. So this is how it looks in general. For each of the primes, we can easily compute the number of people who will count it by subtracting those who will not. And then we take the sum for value of the prime times the number of people here, and in this way we get the results. So to summarize the entire solving process, you generate the primes. Knowing the primes, you can compute the sum as if no child was missing, and then for each missing child, using the prefix sums, you can in constant time subtract its value, and then you get the result. All right? All right, so now sentence. This problem was, I think, very unpopular with this crowd. The first correct solutions only started coming in after a few hours. It was a pretty surprising bit to me because in our local contest, this was one of the problems people were attempting at first. So maybe you've got a little bit of other preparation than our guys do because, for example, in our country, the square count problem usually took them longer and they preferred to play around with this one. So anyway, in this problem, we have a bunch of sentences like this. That sentence 17 is saying, sentence 47 is true, or sentence 23 is false. The thing we see is that this somehow creates the idea of asymmetry, because this seems to be like an implication. One sentence is saying something about the other. What actually happens here is that the relation between the two sentences is symmetric, because what this sentence is saying us is that the sentences 17 and 47 must have the same truth value. If 17 is true, then what it's saying is true, and 47 must be true as well. And if 47 is true, then 17 is a true sentence, because 47 is true, so 17 must be true as well. And if 17 is false, then 47 must be false, and vice versa. So if we see this, a sentence claiming that some other sentence or maybe itself is true, we know that these two sentences must have the same truth value. And similarly, if we see a statement that something is false, then the sentences, in our case 18 and 23, must have the opposing truth values. And with this observation, the problem becomes almost trivial. So what we are doing is we are coloring the sentences using two colors. So we can go along the list of sentences, imagine it as a graph. Each sentence is a vertex in the graph. And we are coloring the sentences using red and blue. And right now we don't know whether red is true and blue is false and vice versa. We are just trying to find a coloring that will match all of these rules. So each time we encounter a sentence that doesn't have a color yet, we color it red, and then we run, for example, a breadth-first search. And each time we are traversing a true edge, we keep the same color. Each time we are traversing a false edge, we switch the color to the opposite one, and we are checking for contradictions. So if we had sentences 1, 2, and 3, and these must be equal, and these must be equal, and these must be unequal, then this one will be colored red, then this one will be colored red, then this one will be colored red, and then when processing this edge, we would find a contradiction. So at the moment we find a contradiction, we can output that the entire set of sentences is unsatisfiable, and we are done. If we find no contradictions, what we need to do is we need, for each of the connected components separately, we need to decide whether red is false and blue is true or otherwise. So each time we finish coloring a component, we take the number of red vertices, number of blue vertices, and as we want to maximize the number of true statements, the color which has the majority is assigned true, and the other color will become false. All right, any questions about this problem? Nope. All right. Great game. All right, so what we have in this problem is a grid. Each cell of the grid contains some payoff, some number of points, some value. 4, 7, 3, 5. 8, 14, 12, 47, 1, 2, 3, 0, another 0, 4, 11, and the 1. And now the players are alternately playing a game in which one of them always picks a row and the other one always picks a column, and the intersection is what matters, right? So this is actually a game that is interesting only for the second player, because the second player has the ultimate strategy. He can, well, clearly the second player can only pick each of the columns once. So out of each column he can only get one value, and he will be picking different columns for different rows picked by the first player. So also in each of the rows he can get only one value. So this basically means that what he can get is some permutation in this matrix. This is something similar to when we are computing a determinant of the matrix. So in each row and in each column you can pick one cell. And it turns out that out of these selections, which are the possible outcomes of the game, the second player can choose any single one of them and reach this. Because, for example, if I choose these columns, then what can I do as a second player? Each time the first player picks a row, I will pick the column that contains my choice. So if he starts, for example, here, I will move here and get the 47. If he now picks this row, I will pick this column and get the 0, and so on. So in order to compute the result of the game, if both players play perfectly, what we need to do is we need to find such a set of cells with the largest possible sum. And the trick in this problem is to realize that if we see a grid, then we can view this grid as a bipartite graph. The rows of the grid can be one partition of the graph, and the columns can be the second partition. So in this case, we have row 1, row 2, row 3, and row 4. We have column 1, column 2, column 3, column 4. And now each of the cells in the matrix corresponds to an edge in this graph. So for example, between row 2 and column 4, there is an edge of weight 47, and so on. Row 3 and column 3 is 3, and so on, and we will get a complete bipartite graph. And now, choosing such a set of edges in the graph is this is a set of edges that covers exactly once each of the columns and exactly once each of the rows. So in this graph point of view, on the same problem, what we get is we are choosing a matching in this graph. So this problem, which started as a discrete matrix problem with looking for some combination of rows and columns, suddenly turns into a graph problem. We have a bipartite graph, and we are looking for the maximum weight matching. And this can be computed in polynomial time. The easiest way to do so, and the only way I remember and can do in the contest, is very simple. You start with an empty matching, which has cost 0, and then you will improve this matching one edge at a time by looking always for the most expensive augmenting path. And it can be proved that if you are in each step using the most expensive augmenting path, the one that improves the weight of the matching by the most, then after each number of steps you will have the maximum weight matching with the given number of edges. So in this case, we will n times run the search for the best augmenting path, and each time we will create a better and a better matching until we end up with the optimal one. To find the best augmenting path, you can use, for example, Bellman-Ford algorithm, because there will be some negative edges corresponding to dropping some edge that was in the matching away. And I believe the overall time complexity of the solution is then n to the power of 4 if implemented like this. There are more efficient solutions. If you can compute the maximum wave matching using a battery algorithm, it can be n to the third only or something like that. I believe using the Hungarian algorithm can give you this time complexity. All right, any questions about this problem? Nope. All right, so problem number 6, I believe, integer power. What we are given is a set of queries, and each query is take the natural numbers from the interval from A to B inclusive. For each of these numbers, compute its power, and then return the sum of these powers, where the power of a number is the largest k, such that the number is equal to something to the kth. Once again, there are several standard tricks that can be used in this problem. First of all, to get rid of such queries with some interval starting somewhere, ending somewhere, we can only focus on queries that look like this, because once we can answer such queries from 1 to some place, we can answer the queries from A to B very easily. You take the answer for this query and you subtract the answer for the query from 1 to A minus 1, right? So this should be an automatic first step if you see a problem like this. Don't bother about two boundaries. You can only focus on the top boundary, and the bottom boundary can be ignored. So now we have a slightly easier problem. Now we are considering the numbers from 1 to some given n, and we want to compute the sum of their powers. And once again, we will use the combinatorial trick I already mentioned. We will count it in a different way. Instead of counting it one number by a number, which cannot be done because n can be up to 10 to the, I think, 15 or something like that was in the problem statement. N can be very large, so we cannot do this by counting it one number at a time. We have to count it in the opposite direction. So the crucial observation here is the powers of numbers tend to be very small. The maximum power we can encounter is less than 60, because this is clearly less than 2 to 64. The n will fit into a 64-bit integer variable. So no number in this set can have a power larger than 64. And what we now can do is we can take a look at the set, and then we can start asking questions. How many numbers in this set have power 64? How many numbers have power 63, 62, 61, and so on until 2? And when we can answer these questions, then we are done, because we take the count of numbers with power 64 times 64 plus the count of those that have power 63 times 63, and so on. And when we know all their counts, when we can fill such a table that power 64, 63, 62, and so on until 2, if we can fill all of these cells, then we can also fill the last remaining cell, which are the numbers of power 1, which are not even squares. And this can easily be filled by n minus some of these other values. So these are the values we need to compute for each possible power, the count of numbers in this set that have this power. So starting at the bottom is pretty easy. So if we ask a question, how many numbers have power 47, then how do these numbers look like? It can be 2 to the 47, 3 to the 47, 4 to the 47, and so on, until we exceed this n. And this will happen for the large powers very quickly. And even for the smaller powers, we can check this easily using some logarithms or so. So what we are solving is x to the k must be less or equal to the given n. If we take for example, a natural logarithm of both sides, we get that k times ln x must be less than or equal to ln n. And solving this for x can be done easily, and then we can, in order to be sure about the plus minus ones, we can compute the values exactly and compare them. All right, so the only thing that remains is to avoid double counting. This could actually happen because, for example, if we count some number to the 32, then we don't want to count the same number as having power 16. If we are counting the numbers which are 16th powers of something, then among these numbers, we will also count all the numbers that are 32nd powers of something else. And this, we want to avoid this double counting, and this can be easily done using inclusion and exclusion. So what we will be doing is we will be computing these values bottom up. And when computing a given cell, so for example, we want to know how many numbers in the set 1 through n have power exactly equal to 3. This is the question we want to answer. And how to do this? Well, in the first step, we will solve the equation I had here. So we will find the largest x such that the x to the third is still less than or equal to n. So we know that there are at most x numbers that have power exactly 3. Why is it at most? Because some of these numbers will actually be larger than third powers of something. Among these numbers, there will be numbers that are 6th powers, 9th powers, 12th powers, and so on. So these we need to subtract. So we will take this x, and we will subtract the 6th powers, the 9th powers, the 12th powers, and so on. And this will give us the count of the numbers that are exactly third powers. So in this way, we compute this table, and from this table, we can easily compute the actual answer. All right. Did this make sense? Any questions? Great. All right, the divisor cycle. This was actually I first encountered this problem as a math problem in the Putnam competition. This is a college mathematical competition in the United States. And I decided to rewrite it as a programming problem. So what we are given is a number n, and we are supposed to arrange all of the divisors of n into one single cycle, such that no two adjacent numbers will have a common divisor of 1 only. So, for example, if n is 12, then the divisors of 12 are 2, 3, 4, 6, and 12. We ignore the 1 as given by problem statement, and right now we can arrange these numbers as 2, 4, 12, 3, 6, and back. And now if we take a look then for each of the two numbers that are adjacent, if we compute the greatest common divisor, it will never be 1. It will always be something more. Here it is 2, here it is 4, a 3, and here it is a 2 again. This order doesn't work because between 2 and 3 there is no common divisor. So there are only some orders that work, and sometimes, as we've seen in the examples in the problem statement, none of the orders work. It turns out that for almost any number, there is such an order and can be constructed quite easily. So first of all, let's assume that we have the prime factorization of the number n. So it's p1 to alpha 1 times and so on times pk to alpha k, where all these p's are pairwise distinct primes and the alphas are some powers. So what we can do now is we can build a circle like this. We can take p1, p2, p2, p3, p3, p4, and so on, pn, p1, and back here. So right now we took some of the divisors and we placed them on a circle. And what we got now is a circle onto which we can place the remaining divisors, because each of the remaining divisors, other than 1, is divisible by at least one of the primes. So for each of the remaining divisors that are currently not on this circle, what you can do, you can pick one of the primes in its prime decomposition and place it on the corresponding part of this circle. So this part will contain divisors divisible by p1, right? This number is divisible by p1, this number is divisible by p1, so we can take all other divisors that are divisible by p1 and place them here in any order. Now we got rid of all the divisors that are divisible by p1, so we take all the remaining ones that are divisible by p2 and we place them here. And so on. So this shows one possible construction that almost always works. The only case when it doesn't work are n's of the form p1 times p2. This is the only case when the construction fails, because now there are only 3 divisors, p1, p2, and p1, p2, and in this case it cannot be done. In any other case, I believe the task is solvable. So that's probably everything. Yeah, so this is basically like a play around problem. This doesn't have to be the only construction in which the cycle can be done. I can imagine other approaches, but this was the one I found, and it's reasonably easy to implement. One other thing that's good to know is that in order to list all of the divisors of n, if you only have to process a single number, it's usually overkill to try to get, for example, to make the C's of Eratosthenes to get prime numbers and to factorize it using those numbers. You can easily run a cycle until the square root of n and check everything. If you only have to, in this problem we needed the primes anyway, at least in some sense, so this wasn't such a great gain, but if you only need to generate the divisors of n, it's easiest to go from 1 to square root of n, and each time you find a divisor d that divides n, then you can output d, and you can output n divided by d as 2 of the divisors. All right, any questions? If not, then we are moving to the next and the last problem for this session. And the last problem was called onmatica, or square root of a matrix. So what we had is we were supposed to find the matrix such that the kth power of the matrix is the identity, and this matrix A has to be, in some sense, non-trivial. Now the trick here is to remember something from your geometry, and maybe linear algebra. Each such matrix, well, first of all, in order for this equation to hold, the matrix A has to be regular. Because if we were to lose dimensions, then by taking the kth power of this matrix, we will lose even more dimensions, and we cannot produce identity which is a regular transformation. So this has to be some regular transformation in the plane, or well, in the n-dimensional space. And if we do this transformation k times after another, then we have to get the original state. So what is a simple transformation that k times repeated gets you to the original state? The easiest to imagine it is in the plane. So we only have two coordinates, and you will do the same operation k times, and you want to get into exactly the situation when you started. Well, the answer is rotation. If you take the plane and rotate the entire plane by the angle 2 pi over k, this is exactly the transformation you need, because after rotation k times, you will get to the same state where you started. So basically what this task boils down to is, in the n-dimensional space, produce a suitable rotation matrix. Now the only trick that remained was to make sure you will never get entry equal to 1 in your matrix. This is usually easily done, but the two problems you could encounter are, the first problem is what happens if n is odd. Because if n is even, then you can easily construct an n by n rotation matrix by taking 2 by 2 rotation matrices like this. So you will separately rotate the first two coordinates, the second two coordinates, and so on. And everything works. But if n would be odd, then this approach doesn't work. You would get a 1 in the last row and column, and this is something you don't want. So this had to be addressed somehow. And the other problem was k equal to 4. Because what happens when k is equal to 4, we are rotating by exactly 90 degrees, pi half radians. And in this case, the rotation matrix, well, the usual rotation matrix looks like this. The vector 1, 0 gets rotated to cosine of phi and sine of phi. And here it's minus sine and cosine. I hope I got the signs right. So this is the basic rotation matrix. And now if you substitute phi equal to pi over 2, then you would get a 1 here, I think. And this would not be the thing you need. So there are two possible approaches how to get rid of this problem. One of them is handling the case k equal 4 separately, and in this case providing a 3 by 3 rotation matrix. But the other trick how this can be done is we will not rotate along the coordinate axis, but we will rotate along a randomly chosen axis that will change all of the coordinates. The trick here is, what we can take is the matrix B that looks like this. It's the cosine, sine, minus sine, cosine. So here in the upper left corner is the rotation of the first two coordinates, and all of the remaining coordinates are remaining unchanged, and the rest of the entries are zeros. So this is a matrix that just does the rotation of the first two coordinates. And now, if we take any regular matrix A, then what will be this? This will once again be a matrix with the property we need, because its kth power will still be the identity. We do some regular transformation. Basically, we choose a random axis. We do the rotation, and then we do the original transformation back. If you raise this to the kth power, what you will get is A b, a to the minus 1, a, b, a to the minus 1, and so on. A, b, a to the minus 1. And now each of these will produce an identity. So you will get a, b to the k, a to the minus 1. This is the identity. So this is a to the minus 1. So it is the identity. So this is some algebra exercise. So we can take any random regular matrix A and its inverse, and by multiplying these three matrices, we will get a random rotation matrix that does the rotation along a single random axis, and this matrix will surely work. The easiest way to generate A and A to the minus 1, so a matrix and its inverse, is do both at the same time. So you start with an identity matrix and an identity matrix, and now you start to make random changes in one of them and the corresponding changes in the other one to keep it the inverse of the previous one. Another way would be to generate a random regular matrix and then to use Gaussian elimination to compute its inverse. Well, basically, if you are given a matrix and you have to compute the inverse, what you are doing is you take the two matrices, you take the matrix A, and you take the identity, and now you will be doing the same operations on both of the matrices, and you are trying to change this matrix into identity, and at the same time the identity will change into the inverse matrix.
The only case in which you should print impossible is when the matrix size is 1. Is that right?
If I remember the problem correctly, the constraints in the problem statement were chosen in such a way that you actually never had to print impossible, and was, I think, guaranteed to be at least 2. So it was just to mislead you.
Do you need A and the inverse, or just B? Why can we just do just B?
You cannot use just the B because one of the constraints in the problem statement was that the matrix that you output must not contain any ones. You must guarantee that all of the entries in the matrix will be different. So basically you take the matrix B that does contain ones and you multiply it by something random to get rid of these. So basically this was a nasty problem testing your college knowledge of algebra, and only a few people so far got it right. So don't worry if you didn't. All right. So I think that's all for today. Thanks for your attention.